great pleasure to introduce Luciano Rezzolla, today's speaker. He's one of the pioneers of numerical relativity, and he has led very important contributions in studying black hole mergers, neutron star mergers, and jet production. These have brought him to be one of the leaders of the project Black Hole Cam, which in connection with the Event Horizon Telescope gave us the image of M87. And I think that Luciano will talk about this and more today. He has received several prizes, including the Carlos Farshid Prize, the NSF Diamond Achievement Award, and the Breakthrough Prize in Fundamental Physics, shared with the Event Horizon Telescope collaboration. He's a professor of theoretical astrophysics at the University of Frankfurt, and he will talk today about imaging a supermassive black hole, if you haven't changed the title.
I haven't. Okay, thank you very much, Marta. And thank you all for the kind invitation. I hope you can see my screen. It's a pleasure to be here giving you this presentation. I would have very much preferred to be there in person for a number of reasons. The first one is that I am tired, as you all are, of these Zoom interactions. But I have to teach at 12 exactly, and I've already moved it a little bit, 12:15, so that you know, I can have to take some questions. And our university has been very, very strict about, you know, pushing things around now that we have gone back to teaching in presence. And so I really couldn't just take these days off. Unfortunately, you know, the way the lectures are scheduled is something that is decided at last minute. So I didn't know when I accepted it on Friday, I would be teaching at 12. So believe me, I would have very much preferred to spend a weekend in Paris than here. So this is what I will tell you about. How do we image a supermassive black hole from an observational point of view? This may be useful for those like me who didn't know how you actually take a picture of a black hole from an observational point of view. And then I will tell you a little bit about how you do theory about this image and how you compare then theory and observations. And because I am a theorist and I think, you know, the doubt is always nurturing in me, I'll tell you about alternatives to Einstein and even to black holes, whether or not we should or must consider them. Okay, so first of all, a very basic problem. Black holes are the most compact objects in nature. You can't possibly concentrate energy or matter into a smaller volume, okay? All right, and the second is that black holes are at astronomical distances, which is probably a good thing for us. But this also means that if you want to take an image, well, this object has to be resolvable on the sky. So its projected size on the sky has to be something that with one telescope, whatever telescope you decide to use, has to be able to resolve it. And, you know, if you put all of these conditions together, you only have a solution to this. And that is, you need very massive black holes because their size is the largest possible. And they have to be sufficiently close to us because balancing distance with size, you may end up with the size on the sky, the projected size on the sky, that is accessible to a given telescope. And that's exactly the kind of, you know, back of the envelope calculation that we have done, well, a few years back, to realize that, you know, out of this list of possible candidates, there is a handful of possible candidates. And all of them have, you know, an uncertainty in the actual mass. So I say that they have to be very massive, but of course we don't know what is their mass. So even when we, sorry, we looked at M87, we didn't really know if we would be able to resolve them. So this is M87. It's an elliptical galaxy. It's in the central Virgo cluster, about 55 million years. And if you look at it in the optical, it looks as this beautiful filament coming out. You know, at the beginning, people thought this was a comet. We know that that's actually a not relativistic jet. If you look at the same image with the same scale, but now you look at it in the radio, you see it's much bigger. It's emitting from a much larger region, and that's pretty typical, because galaxies tend to, you know, produce highly energetic electrons, and this then will shine in the radio. And so if you look at it with a radio map at few centimeters, that's what you would see. And then using a technique which we have exploited to the extreme, you can zoom in into these objects. And so if you go into now a centimeter wavelength, you can do a zoom in of this image, and you can see the jet now very, very clearly. You can see when it stops interacting with the intergalactic medium. And you can further zoom in near the launching site, and you can see there are these spots. You can further concentrate your attention to the very inner part of the jet. And nowadays, astronomers know all of these little features here, and they study in great detail how they vary in time. And this is actually how they learn that there is matter moving at relativistic speeds, ultra-relativistic speeds. And just to give you an idea of the kind of resolution we wanted to have, you know, this is the resolution we want to have, and we have achieved with the Event Horizon Telescope. So it's really a jump in terms of our ability to use this technique, which is not a new technique, it's an old technique just used to the extreme. So how do you use this technique? You need one equation, which is very simple. Actually, this is not true only for this. Any astronomical observation relies on this. If you want to take an image of an object with a given resolution, this is essentially given by the ratio between the wavelength at which you are observing and telescope size. And you know, if you are a theorist like myself, you would say, well, okay, then let's take the smallest wavelength possible. Let's use gamma rays. And you know, then an observer would tell you, oh, you're really impossible. You don't know anything about emission. Gamma rays are emitted, of course, but they are trapped. They are trapped very close to the black hole. They have no chance of reaching us. So you need wavelengths that actually are able to reach us. And so you end up with radio waves. And if you have radio waves, you want to have a large radio telescope. Telescopes, the biggest telescopes we have are radio telescopes. That's because they can be built to be quite large. In fact, the largest one is in China, fast, as 500-meter diameter. But even if you have 500 meter and you put it there, denominator, you're not going to get the resolution that we need, which is tens of a micro arc second. However, and that is where you can use this technique, VLBI, very long baseline interferometry. Essentially, you build a telescope which is as big as the whole planet. And the way you do this is that you take a few telescopes scattered across the world. They are not particularly large. They are 20, 30 meters in diameter, but they have very high frequency receivers because these are very high frequency radio waves. And there is one in France, NOIMA, which is very useful. And then you can put in an interferometric pattern telescope, say at Hawaii, and one in Arizona. And so you can have a telescope which is, at least in principle, as large as the distance between Hawaii and Arizona, which is 3,000 kilometers or so. Now, if you think a little bit about this, you start thinking, well, there is something fishy here. Why is it that I don't do this for any astronomical observation? Why can't I do the same with optical telescope? Well, you can. The problem is that you need to make sure that you are observing exactly the same wavefront. And this is much harder for an optical wavelength. You can do this in terms of radio waves because they are much more coherent, longer. And in particular, you have to make sure that you're really getting the same wavefront. And for this to happen, it's not sufficient to measure an electric field when it arrives in Arizona. You also want to measure the time, the exact time when this happens. And so you need an atomic clock here and elsewhere. So all of these telescopes have not only very high frequency receivers, they also have very precise atomic clocks. They have very precise mappings of how the separation changes with time because the surface of the Earth is also moving all over the place. And only after that, you are able to actually do interferometry and reproduce therefore the image. And so if you then have another telescope, say in California, then you have another baseline, and then you have another resolution. So you can build an image with multiple resolutions. And if you put all of them into a network, then you have reached two important results. The first one is that you have many different baselines, and so you have different resolutions at which you are observing. And the second one is that they are scattered in at different longitudes. And this means that as the planet rotates, you can always, or on a much longer time scale, observe the source. Because if you were just, say, in the American continent, at one point, the American continent would be eclipsed. You would not see the source anymore, and so you would lose precious time. And that is why it's important to have them across the whole surface of the planet. And of course, unfortunately, we don't have anything here in the Far East, but that would also be very useful. So how do you do the observations? As I was explaining, you take different telescopes, say IRAM in France, APEX and ALMA in Chile, and so on, and you have a certain baseline, which are colored with a given color. And these will measure the intensity in the sky, the projected intensity in projected coordinates x, y in the sky. And this produces a complex function, which is called the visibility. And this you have to think of as the two-dimensional equivalent of a Fourier transform. It's just that you are not transforming in between time and frequency, you are transforming in positions because you're building an image. And any baseline at any time is a point, and then as the Earth rotates, the baseline changes, and so these become tracks. And once you have a given track in this, which is called the UV plane, you can produce an image like the one I'm showing you. And if you wait for a longer time, your tracks will become longer, you can feel better the UV plane, and your image will become sharper. That's exactly the basic functioning. And this is what I'm showing you in this movie. At the beginning, you have just a few telescopes, very few tracks. And as time goes on, you can put this information together and increase the precision at which you're seeing the image. Now, if you follow me so far, you probably appreciate that this space is sparsely covered. Again, going back to what is more familiar to all of us, if you think about Fourier transform in frequency, it is as if you have a power spectral density, which is chunked in disjoint regions of the frequency. And from these disjoint regions, you would like to recover a time-dependent function. You can do this, but you have to make some assumptions. And there are some assumptions that go into going from this visibility into an image, because as I said, the coverage is sparse. This is something that is important and which we wanted to avoid. We wanted to avoid a bias of any type. And so what we have done is we have created 4 teams. Here is, you can see one of them, each of which worked blindly with respect to the others. And they were allowed to, they had all the same data, but they were allowed to use any assumption that they wanted about the data, any software that they wanted to use for the data, even newly developed software, and then come up with the image. And this is what happened after 2 weeks of blind work. The 4 teams came up with these 4 images. And this is where, at this point, really, this was a phase transition in our expectation, because all of a sudden, these different teams provided images that were different, but were comparable. And they were all showing that there is a ring with a depression in intensity. And of course, time has gone on. These people then have joined together forces. They have agreed on what are the correct way of doing things that everybody agrees on. And these are what they call the consensus images. And so, as you can see, these are 4 images, because we had about 8 days of observations, but all of them not all of them were good. And so you produce these 4 images. And what you can see is that they are different, but they are very similar. And that's what you would expect, because given the mass of this object, billion solar masses, the time scale for changes are much, much longer than a few days. At the same time, if you think about the time scale associated with, say, particle motion near the event horizon, that's of the order of a few days, or less than a day, actually. And so the fact that this image and this image are not the same is what you would expect on the basis of these very simple arguments. And so, this is what I, as a theorist, was ended in. And I was asked to, together with my colleagues, of course, to come up with a measurement. Well, first of all, an explanation of what is it that we're seeing, why it looks like that, and then with a measurement. And how do you do this? Well, I'm very proud as European that we received this grant, which allowed us to do this work. And not only allowed us to do this work, it actually really created an avalanche effect in the Event Horizon telescope, because as soon as we got this funding, NSF decided to put in an equivalent amount of money into the US system, and this then really lift off the project, because sufficient manpower was available into the system for doing this analysis. And there are 3 steps that are needed in this analysis as a theorist. The first one is GRMHD simulations in arbitrary spacetimes. Essentially, you need to understand what happens to matter falling onto a black hole. The second one is ray-traced radiative transfer calculations, and then the creation of deconvolved images. Essentially, once you know what happens to matter falling onto the black hole, you want to study and understand how light from this matter shines. And then you want a comparison with the observations, of course. And, in Frankfurt, we have developed 3 different codes that do these 3 different steps in the process. And the only merit goes to these people that have spent hours and hours doing these codes. And let me explain what are the equations we need to solve. Luckily for us, in this problem, I don't need to worry about the Anson's equation. This is because the masses of the black hole are so much more than anything else falling onto it that I can ignore any change in the space-time. And so I'm left with conservation of energy and momentum, conservation of mass, an equation of state. And then I need, because I have magnetic fields, I need additional Maxwell equations. And the energy momentum tensor is the combination of all of these different components. And in addition, and this is where things get more complicated, I need to solve for the radiative transfer equation. This is essentially a Boltzmann equation for distribution of photons. And so I will have to take into account some intensity and how it is absorbed and emitted along a path followed by light. And this has to be done in the background spacetime. If you want to understand what happens, if you want to see what is the result of the first step, let me show you a typical GRMHD simulation. This is a curved black hole, highly spinning, and I'm using a curve field coordinates, a magnetorotational unstable torus, so that we can trigger accretion. You start with the torus, which is axis symmetric, and then soon after you will develop an instability, and this drives accretion. I'm showing you in red, yellow, the rest mass density, and in light blue, what we call the magnetization, the ratio between magnetic energy and rest mass. So blue is where there is very little rest mass and a lot of magnetic field. And you can see this is really in a very small region near the polar axis. As the simulation will start again, you will see that the accretion is not a static or stationary process. It's very chaotic. There are times where the mass accretion rate goes up and other where it goes down. It's a bit like being close to a waterfall. Overall, the waterfall will bring the same amount of water down, but there's going to be times where it's more and other where it's less. This is the inclination at which we think we're looking at M87. So there's one jet that's coming towards us, and the plane of the disk is very much almost face on. Now, this is the emission at 1.3 millimeters. So this, if you had radio-sensitive eyes, this is what you would see. A very precise radio-sensitive eyes. Now, it looks like a ring, okay? But it's just misleading. It's because we are in this very special inclination. If we start rotating around this radiation field, you will see is very complex. And in practice, telescopes have a finite resolution, and this is what they would see. So overall, they would see something that over a time scale of a few tens of hours flickers, and with one side which is brighter than the other. And that's what we see. Okay, so already at this point, you can conclude that the reason why it looks like so is because we are observing an accretion disk onto a black hole, and that this disk is oriented in this manner. This is just an idea of the whole domain. So that's step number one, understanding what happens to matter. Step number two is tracing photons. We used to thinking that light travels in straight lines. That's because we live in a locally flat space-time. But near a black hole, that's not the case. So if you imagine that you have a black hole and you have a thin disk, and you want to take a photo, then you will find something that Luminet in 73 described beautifully in a paper. So you would first see the direct image, all the photons moving directly, and so you would see the first portion of the disk. But there are going to be photons that, in principle, are just emitted orthogonally to the surface, but would never reach you. But actually they do because space-time is curved and curves this. So you would see this part of the disk as well. And to make things even more interesting, nothing prevents to having an indirect or high-order image, we say, coming from the sheet below the disk. So this part over here is actually the sheet below the disk. If you like science fiction, you probably you know what I'm talking about. This is an image from Interstellar. It's not exact, has some flaws, but it is very accurate. And what you can see now, maybe you can understand, you see the part of the disk which is in front of the astronauts, you see the part of the disk which is behind the black hole, and the part of the disk which is below. You also see this very thin and bright ring. This is the photon ring. I will explain this better. And you see this dark region here. This is not the event horizon. This is what we call the shadow, and I'll explain that. For the time being, though, the lesson you have to learn is that if you have to hide, don't go behind a black hole. That doesn't help. Now, as I explained, and as is wrong in Interstellar, the disk is geometrically thick. It is optically thin, but geometrically thin. And so the kind of disk that you have to imagine is like so. And now I'm rotating, so you can appreciate that according to rotation, you may have two parts of the shadow, or you may have a single shadow. And also that unless you are really exactly face on, there's always an asymmetry in the luminosity. And this is because there's always a region where, which is moving towards us or away from us. And so where the intensity is decreased. So this is a very basic piece of physics. No matter what you do, you will have to take that into account. You can't have symmetric images unless you are really face on. Now the shadow, this is, people tend to confuse shadow and event horizon, but let me explain the difference. Suppose that you have a black hole and you have a source of light. Then what is going to happen is there's going to be photons that are going to be emitted by this light, and you are here, you're an observer. There are going to be photons that hit the event horizon straight on. They have the impact parameter, zero impact parameter with respect to the event horizon. But there are going to be other photons that are not hitting the event horizon, but are within an important orbit, which is the unstable photon circular orbit. And these photons are doomed to be also accreted, absorbed after some revolutions. And so if you are an observer here, you will see a deficit of light. There's going to be some light that you should be seeing from here, and you just don't get. And this is essentially the shadow. So to fix ideas and considering Schwarzschild, the event horizon is 2m, the photon orbit is 3m, this photon circular orbit, and the shadow is the impact parameter at this radius, and is roughly 5m, 5.2. Now, you can also appreciate an important point people tend to miss is suppose you produce a photon here and you emit it, okay, towards the observer. This photon wouldn't have any problem reaching the observer. There's nothing preventing it. That is why the shadow is not necessarily a black region. It's just a region where you will see less light because some of the light will be absorbed by the black hole. But anything which is emitted between the black hole and us will reach us, no problem. Okay, so this is all basic theory. If you want to explain those images, you have to explore all the possible space of parameters. And here you have black hole mass and spin if you're in GR. You can think about black holes in other theories of gravity. You can think about alternatives to black holes, compact objects that don't have an horizon, that have or do not have a surface. Then you also have to worry about the plasma dynamics and properties. We know that there are at least two different classes of accretion. One is called sane, the other one is called mad. The first one is the standard accretion. The second one is a magnetically arrested. Essentially, they differ by the amount of magnetic field which is advected to the black hole. And these are much more magnetized plasma, and the magnetization will be so large that accretion actually even stops. That's why they're called magnetically arrested. And we don't know really which of the two is the right one, at least because they are potentially both right. And then there is the light dynamics and properties. We know that it has to be synchrotron emission, has to come from electrons going around magnetic fields. But we don't know where the electrons are because we don't track electrons, we track ions. And then, of course, this is a purely geometrical orientation problem. You have two free angles, you have to know how to constrain them. The electron thermodynamics is, in my view, one of the most serious difficulties. As I said, we know it has to be synchrotron because we get it at 1.3. But all of our simulations evolve the ions, they evolve the heavy part of the fluid. And so we know everything about the temperature distribution of the ions, but we don't know what is the energy or temperature distribution of the electrons. And it's them that is producing the radiation. So how do you get around this? Well, the first one you can say, let's assume the temperature distribution is thermal. Once I know the temperature, I know exactly what is the energy distribution, a Planckian. Sorry, not a Planckian, it's a Maxwellian. This is the thermal distribution of the electrons, not of the light. Then you can say, I know the temperature of the ion because I calculated. I create an analytic relation that tells me the temperature of the electrons. And I model this in a very simple way. I have a parameter, which is the plasma, the beta plasma parameter, which is the ratio between the gas and the magnetic pressure. And then you have essentially one coefficient, which allows you to go around and put all of your emission in the disk or in the jet, depending on what is this value of R high. And so this is the prescription we've used in the papers. And we use a number of values for R high. So in my talk later on, you will see I often use this coefficient R high. Now you may think that this is very crude. It is crude, but it is analytic. And so it's very fast and allows us to produce a lot of different scenarios rather simply. And later on, we've done a much better job. There's a paper by Yosuke Mizuno, who has looked at how things would differ if you use a more complex energy distribution, coming maybe from turbulent heating or magnetic reconnection. And you find out actually that this very simple formula is a very effective way of capturing all of these effects, which are microphysically different, but in practice appear the same in terms of energy distributions. So we have carried out a number of simulations, about 50 high resolution simulations. Half of them were done here in Frankfurt. Painting the electrons in different places, we have produced 400 scenarios. And this image just gives you an idea of some of these scenarios. They are maybe all the same inclination. So, but you can imagine that all of this has to be changed, the inclination. But you can see that there are counter-rotating black holes, there are co-rotating black holes, there are small shadows, large shadows. All of this has to be tuned. You can produce tens of thousands of images. This is a summary of how the image looked. These are averages. So you take those simulations, you average them, that is what you will see. And this is an interesting first point. You see that the most important thing is the appearance of the light ring. That's because most of the light tends to spend a lot of time there. All the other features are fluctuating, and so they average out. But these are constant, steady emission. And so that's why they look they're always present. But of course, there are differences coming from sane models and mad models, and we can't compare these. We have to compare snapshots. Now, a question that I hope no one will ask me, or rather to prevent an embarrassing answer. If you ask me where do the millimeter photons come from, I would say I don't know. And that's because there is a lot of degeneracy, and I will explain this a little bit better. But to give you an idea, take a Kerr black hole, and you have this parameter high, and you can take it between 10 and 160, which are the ranges we used. Here I'm showing a black hole. This is the event horizon. This is the photon region. Is the equivalent of the photon ring for a rotating black hole. In the case of rotating black hole, it's not just a single surface, it becomes a region. Here is the ISCO. And you can imagine we are down here. So R high, small R high, you see that most of the light comes from the disk. If you change R high, most of the light comes from the jet, okay? And particularly from the, what do we call the jet sheet, is the outer boundary of the jet. And this is true, although less significantly, also for a mad type of accretion. This is a sane and this is a mad. You can see that, again, playing with R high, I can put more light into the jet and less into the disk. And I can show you the same for a counter-rotating black hole, where this degeneracy is even worse, okay? So in practice, it's very difficult, once you have an image, to know where the light comes from. To make this even clearer, suppose you have these 4 images. These are 4 images, and you ask yourself, well, tell me, where does the light come from? Because these are images I built, theoretically, I can split them. I can split them into 3 parts. I can split them into the midplane, so roughly the disk. I can put them into the jet near me, or the jet which is moving away from me. You may think, well, how can I possibly get light from the jet moving away? Don't forget, this is a curved space-time. You can get light there, from there. And here these are different rows, different models with mad and sane, small R high, large R high. And if you look at this as a matrix, you see that this matrix is not always it's not always the mid-plane column that is filled. Sometimes you have that even the far side jet is actually the one contributing to the largest amount of radiation. So in this image over here, most of the light doesn't come from the disk, doesn't come from the near jet, actually comes from the far side jet. So this degeneracy is inevitable. That's because all we're having is an image. And we have to do the best we can in this respect. So in this way, we built 60,000 images, and then we had to compare these 60,000 images with the one coming from the 4 I've shown you. And there are algorithms that allow you to do this. These are genetic algorithms or Markov chain Monte Carlo. I introduced this visibility complex function. The real and imaginary part are called the closure phases and the visibility amplitude. And I'm showing you what we do in this example. The data is the blue dots, and the model is the green dots. And as a given simulation is produced and then they convolved, will give you a certain distribution in the image space, we call this. Sorry, in the visibility space. And then you can calculate rather straightforwardly a chi-squared between the data and the model, and obtain a distribution of images with certain properties. I like to come up with a different analogy, which brings in an important example. Suppose that you have an image of someone, a human being, and you would like to, and you are at a stadium. The stadium has 60,000 people in it, and you would like to know if the person is in the stadium, and if so, what type of person this is. What you can do is you take this image and you cross-check against all of the images of all the people that are in the stadium. And of course, you're not gonna know for sure whether the person is there. What you can do is obtain a distribution of images that resemble your original one. And so you find these top best matched images. And although you will not have the certainty that the person is there, what you can learn, that there are two things you can learn. The first one is that this person is most likely a woman, because all of the images that have been sampled and that match are of women. And the second thing is that you know that this person most likely has long hair. That's again because all of the matches are people with long hair. So although you don't know whether the person is in the stadium, and although you don't know, if it is any of the best match, you do have two pieces of information that you gain. It's a woman with long hair. And logically, this is not very different from what we have done. This is an example of the match we have obtained. So this is the observations. This is the theoretical model. I know everything about this image. Okay, I know what is producing that. And if you look at it like this, you would say, wow, you know what we have observed. The answer is no, unfortunately, because this happens way too often. This is an example, okay? The images below have mathematically, there are some metric functions that allow you to define how good the match is. And these are all comparable with the observed images. And yet they correspond to completely different black holes. This one is a counter-rotating black hole, minus 0.94. This is a co-rotating black hole, 0.94. This is a Schwarzschild black hole. And the reason why they all match is because they differ in the other elements, in the other degrees of freedom, which are the type of accretion made or sane, or in the electron distributions. The RI is different. So in a way, this is good because, as in the previous case, shows you that you know that all of these images are produced by black holes, and so the observed image is very likely a black hole. It's bad because it blinds you to an important parameter, which is the spin. And in fact, our papers do not report any measurement of the spin. We measure the mass because that allows us, we can measure that robustly. Now, if you're unhappy with this, you can introduce other priors, astronomical priors. And for instance, the jet power, we know how much power there is in the jet. And we know that slowly rotating black holes are not able to match that jet power, okay? And so all the sane models with spin parameter less than 0.5 are to be rejected. And instead, MAD with, most of MADs are fine. If you then put in the X-ray luminosity, again, you have another way of rejecting some of the models. So this doesn't give you a measurement, but already starts to isolate regions of the spin which are incompatible with the observation. Slowly rotating black holes cannot produce what we see. Okay, I'd like to take maybe 10 minutes, 15 minutes to address, how, what do we know in terms of gravity, okay? All of what I've shown you is consistent with a curved black hole in general relativity. And, as far as this being an observational science, you cannot avoid the generative explanations. We can't build black holes and test them. We can only observe them. So how do you go about testing gravity? Well, this is not trivial because there are hundreds of alternatives that are available. And you can have two approaches to this problem. One which is an agnostic approach and one which is agnostic approach. In the first one, you just say, I parameterize and I then compare parameters. And in another one, you say, I know some solution and I check whether these solutions work. So the agnostic approach is the one I have particularly spent some time thinking about. Luckily, we don't need to solve the answers equations, okay? So all we need, we don't need an action for our theory. All we need is a metric function. And to me, a metric function is just a tensor with 6 components, which is a function of certain coordinates. Now, what you can do is you can express any metric in terms of some parameters, AIs and BIs. And this is what we've done together with Roman Konoplia and Alexander Zhidenko. And so in this case, GR is just seen as a reference case, the one in which all of the coefficients are 0. Now, there are many different ways in which you can do this expansion. Most of them fail pretty badly, and that's because they don't use 2 of the tricks we use and that I actually learned when doing binary black holes. The first one is we use coordinate compactification. So instead of doing an expansion in terms of radial coordinates, we do an expansion in terms of a compactified coordinate, where R0 is the position of the horizon. And so you go from having an expansion between 2 and infinity to something between 0 and 1. This is in the Schwarzschild case, and you can do the same in the rotating case. And another one is, maybe a very important one, is that we don't use what most people use, which is a Taylor expansion in M over R. Well, R is the radial coordinate, but rather we use a Padé expansion at the horizon. So we use a continuous fraction approach. This is something I've actually learned from people like Thibaut Damour, and this is particularly useful because after all, you're trying to model a function which has a pole, and these are very good matches for functions having a pole. And if you do this, then essentially with 2, 3 coefficients, you can represent analytically any metric that you want. And so the name of the game is, rather than then checking whether or not an observation matches a given theory, take your observation and translate it into these coefficients. And then you can tell whether or not these coefficients are 0 or non-zero. This is the spirit also in what is called the parameterized post-Newtonian approach. If you want instead to look at agnostic approach, well, we looked at dilaton black holes, we looked at boson stars, and we looked at charged black holes. In this case, it's very different from what I showed you before. Here we have a precise object to compare with, and we check whether or not it matches. So first of all, if you want to ask yourself how a dilaton black hole looks like, you have to make sure that you're comparing comparable things. And a dilaton black hole is a spherically symmetric black hole which has a single parameter. And this means that fixing this parameter, you can fix the spin of the curved black hole, the corresponding curved black hole. So suppose that you have a curved black hole of 0.6, then you can build a dilaton black hole which has either the same horizon size or the same photon orbit or the same ISCO. And this is because you want to compare quantities which are the same. And this is an example of a simulation where on the left you have Kerr, on the right you have dilaton. The match is done at the ISCO. That is why the 2 horizons have different sizes. We think the ISCO is probably the most important quantity to have matched because it's where most of the radiation would come. And if you look at this simulation, you say, well, yeah, they look different. But the point is that you're not going to have simulations to compare with. What you have is images. So you take what that simulation on the right, you pass it through all of the pipeline that you've developed to study Kerr black holes, and you produce an image. So this is a Kerr black hole. This is a dilaton black hole. They're different. But then if you ask yourself, well, if I scramble, would you be able to tell which one is which? And in particular, if you are now looking at something like Sagittarius A star, which also suffers from scattering, then that's what you would observe. Okay. Of course, you can't judge by eye. You need some quantitative metric that tells you how different this guy is from this. And after you do this, you realize that it's not possible to distinguish, given the quality of the data, two black holes. At least none, unless they are really significantly different. And in our case, this black hole is not significantly different. Let's move on to a boson star. A boson star is not a black hole. It doesn't have even a surface. It's an horizon surface object. But people have looked at it in the past because it's interesting, scalar field. We see dark matter in galaxies, why not? What is important is not so much think about how a black hole would look like, but a boson star would look like, but actually how a boson star, which is subject to accretion, would look like. And so it's really important to ask the proper question, how does an accreting boson star look like? And so we have carried out the first simulations of an accreting boson star. You see just the torus, but you have to imagine that there is a boson star around, which I'm not showing. The boson star is taken as a solution of the Klein-Gordon equations with a complex scalar field and a very simple quadratic potential. These are the mass of the boson. And the compactness, which gives you an idea of how compact this object is 6%. It's not huge, but it's a compact object. And if you run exactly the same simulation, what you see is something like so. There is that matter falls in. There is no horizon. Matter can fall in. There is nothing preventing it from falling in. But also it cannot reach r equals 0. And that's because as it falls in, it has to conserve angular momentum. And so we'll encounter a centrifugal barrier. The MRI, which drives accretion, actually is halted near the center because the conditions for MRI change completely. And so essentially the matter there doesn't know where to go, cannot go further in. And so it just moves along the polar axis. This is an example. Left, you have a Schwarzschild black hole. You have a boson star with the same mass. You can see that in the case of a black hole, matter goes in and there it stays. In the case of a boson star, matter goes in and then stays in. It produces this that we call a mini torus. Maybe it's easier to see here. It's this density increase in the form of a torus. And then it just moves out along the polar channels. Once again, we will not have a simulation to judge. We can just compare images. And these are the images. This is a Kerr black hole. This is a boson star. And you can already tell, even with infinite resolution, that they have a different size. The shadow has a different size. And this becomes much more clear if you deconvolve the image with the detectors, with the telescope sensitivity. You can see that this shadow is larger than this shadow over here for the same mass. And of course, you can change the size of the shadow by increasing the mass. But then if you want to match this guy over here in size, you will need too large of a mass, which is not compatible with the observations. So in the light of this, you can conclude that it is possible to distinguish boson stars, accreting boson stars from black holes, at least the boson stars we have looked at. You can also constrain charges. So black holes in different theories or with exotic matter in GR are described with different parameters. Or, people call them hairs or charges. And this is in particular, you can calculate the photon sphere, this quantity over here, as a function of the physical charge. And here I am using a normalized physical charge because these numbers are not always from 0 and 1. But if you normalize it, it is always between 0 and 1. And then you can see how the photon sphere changes as a function of the different charge. And the same happens for the E-score. And now, given what we observed, you can set a size for the shadow radius, an upper limit and a lower limit. And then you can go back to this plot and just, cut out the regions where this part of the region over here and this part of the region over here. And then check which black holes are within this region. And you can see that most black holes are within this region, but there are some black holes like this this doubly charged black hole, which has certain values of the charge, which are incompatible with the observation. So in this exercise, what you learn is that while most pass, some do not, at least for some values of the charges. And then you can convert this in terms of the allowed region for these doubly charged black holes. Those are these doubly charged Boson black hole or a sand black hole. And you can see that, in principle, all of this region is allowed. With the observations, this region has to be excluded. So very high charges are excluded, or a combination of very large charges are excluded. And so you're left with an allowed region, which is still very large, but it's becoming smaller. And the logic is that as the observations improve, then the allowed region will shrink, hopefully going to zero when you have infinite resolution. Okay, I should stop here so that I can take some questions. Let me just recap what is it that I've told you about. This project, European project, has covered all the aspects of these observations and has played a major role in the EHT campaign. We have studied accretion onto Kerr black holes extensively. Essentially, over the course of a couple of years, we have studied Kerr black hole accretion more than was studied in the last 20 years before. We have explored many physical scenarios and thermodynamical regimes. Because everything is consistent with generativity, doesn't mean generativity is right. We need to exclude alternatives to make sure that it's a Kerr black hole. And so we looked at alternatives to Kerr black holes, and we've realized that it's very difficult to distinguish different black holes, but maybe objects without a surface, like boson stars, they are easy to, or say a wormhole, they are easy to exclude. Now, if you think about what is it that EHT has done, it has shown the first evidence of the existence of supermassive black holes, at least in one galaxy. In M87, we've shown that most likely there is a black hole. If you studied ever astronomy, that's the first thing they teach you. So, essentially, we have validated the first lecture of astronomy. But, so far, this was an assumption. Now we know that at least in one galaxy, this is true. And by extension, possibly in all galaxies, at least the largest ones. If you ask me, I think the most important thing is that we have now transformed the event horizon from being a mathematical object, something you work and write on a blackboard, into a concept that you can test. Because all of a sudden, certain ideas can be tested. And if you think about it, this is the essential first step in any scientific effort, the ability to test and validate different hypotheses. So to me, this is the most important result. And I'll stop here, and I thank you for your attention. If you're still there.
Yes, thank you very much, Luciano. This was excellent. So let me open the floor for questions. You can either raise your hand or put the question in the chat if you prefer. So while people think about it, just can you give a very quick explanation on how for a thin disk with high R high, the image is dominated by the far side jet?
Yes. In the same simulations, the jets are thinner. They don't have a very wide opening angle. And so it's easier to get light because you're not moving very far from the black hole. Remember, you're looking near the black hole, okay? And at a certain inclination, you are almost, you are very close to seeing whatever comes from the jet. MAD tend to open up the jet, and so you tend to lose that light over there.
Yeah. So now, Pierre.
Yes. So thank you for your great presentation. I had one comment and I have a question. The first one is, I also thought that the wonderful work that was done around the black hole of our own galaxy also provided evidence of the existence of a supermassive black hole by measuring the orbits of the stars. And I always thought that that and the Event Horizon Telescope were very complementary in that regard. So could you comment on this? And then my question is, it's very clear that the Event Horizon Telescope has provided wonderful results. And as you've said, I mean, it really transformed the Event Horizon from a concept to a testable object. The question I have is, what are the next steps to go deeper and provide more observational evidence to distinguish between the different models that you showed?
So, well, thank you for a comment and a question. Let me first reply to the comment. Gravity is a beautiful experiment, has done a fantastic contribution. But when it comes down to providing evidence of the existence of a black hole, and I think not having imaged anything on the size of the event horizon is not able to actually address this point. And in fact, you know, the Nobel Prize has recognized this in saying that the prize was assigned for determining a dark object in the center of the galaxy. So I think the event horizon is looking at much smaller scale. And while the Event Horizon Telescope hasn't given any evidence of the existence of an event horizon, it can't. An event horizon is a null surface. It is much more convincing that there is an event horizon because we see a shadow. So I think it's the shadow that brings in the event horizon. Orbital motions gives you an idea that there is a very compact object which is not emitting light. But then, you know, especially if you're not a black hole defendant, you will find that that's not an evidence for a black hole. Now about a question, where do we go from here? Well, if you remembered my slide on resolution, you can improve things either by going to smaller wavelengths, so higher frequency, and that's what we're going now towards. We're making observations at 350 gigahertz versus the 230. And the other option is getting a larger planet. Well, you can't really get a larger planet, but you can go out of the planet. You can take satellites and put small radio telescope on these satellites and have VLBI techniques on these satellites. So that's, I think, is really the horizon. Going into space, and then there has been some preliminary work where we have worked out how much would you gain in terms of resolution, and we've shown that in 6 months, over a constellation of 3 satellites on rather low orbits, you can cover the UV plane so densely that essentially you can get a factor 10 in resolution. And so many of the open questions that we have now can be addressed if you have a factor 10 in resolution. But this is space. Space is slow. So far, all of the agencies have ignored us. So it's a long way before we can launch something. But I think that's where the future is.
Thank you.
Françoise?
Yes, thank you very much for a beautiful talk. In fact, I was wondering, would it be possible in the future with the space, or I don't know, but you have shown that all the models for the moment are degenerate, the MED and SANE and so on, but we would like to know where the jet is coming from. Is it from the disk, and what distance from the black hole is the jet coming from? So do you think that after some constraints, we'll be able to do that?
I think so, yeah, I think so. If you want to address this question, you cannot rely on the image only. You have to put in all of your firepower in terms of astronomical observations. This is, as it happens, today there is a paper on the archive where we show that if you do this, if you bring in the match with the SEDs, the spectral energy distribution of M87, and you bring in the large-scale jet morphology, and you bring in the theoretical simulations, then you have a way of saying that MED type of accretion is preferable, and that the spin has to be high, larger than 0.5. So, in astrophysics, if you are stuck with just one image, you can tell little. But if you're putting a lot of more material, then all of a sudden you can be much more sharp in your conclusions. So yeah, that's the way to go. Put in all the information that we have from spectral energy density, variability. This is where all the difficulties and advantages can come in. So this is really the first page of a long book on observing and imaging M87 and other black holes.
But just a very quick one. Would it be possible to do the image of our own galaxy black hole sometime?
So when we did in 2017, don't forget, we published in 2019, but the data was taken in 2017. At the same night, we were collecting data also from Sagittarius A star. We have the data. We've been looking at the data for the last 2 years. And the reason why we haven't published is because it's difficult. And the reason it's difficult because it's highly variable. So the variability in M87 was 20 hours. Variability in Sagittarius A star is 8 minutes. And we integrate over 8 hours. So, all things happen every 8 minutes. And if you want to convince yourself that there is a shadow, you have to have very careful analysis. But we hope that at the beginning of next year, we will publish. The papers are now to be submitted. So probably they'll be reviewed over Christmas time, and then early next year, maybe they will be public.
Thank you very much.
Perhaps one last question from Jean-Pierre before Luciano goes teaching.
Luciano, thank you very much for this excellent talk. And I just would like to tell you that you will have some more work to do about boson stars, because today on AstroPH, there's a paper by Mitch Begelman showing that MRI is supposed to be very active even in the MAD solution. So you have more work to do. Thank you very much.
Yeah, thank you. I haven't seen the paper, but let me get this straight, Jean-Pierre. I'm not saying the MRI is not active. As the matter goes in, it will differ. The angular velocity will differ considerably. And as you get close to the innermost edge of the disk, which is not the ISCO, there's going to be a change in the sign of the derivative of the angular velocity. The angular velocity will no longer decrease outwards. We'll actually have a local peak and then go down. At that point, the MRI doesn't work. So, this is just inevitable. If you think a little about it, it's centrifugal barrier. If you take a fluid element and you accrete it onto a central source of potential, there's going to be an infinite centrifugal potential. So you can't possibly go to R equals 0. And that's...
yeah, okay. But even if you go to R to 0, the matter will be, it won't be bosons. It will be matter, and you would see it anyway. So...
yeah, but okay, maybe.
So I think that, no, it's a very good point, but of course, because you would see the matter. If it's accreting, you would see the matter.
Indeed, you will see the matter, and that's what, let me see if I can, you will see the matter. So the point is that this matter over here, okay, this matter is very close to R equals 0, much deeper in the potential than this matter over here. So you will see the matter, and this black region is not produced because there is an event horizon or because there is a photon ring. It's because there is no matter here. Yeah, so it will look like a shadow, but it's not going to be a shadow. And this object, so this little intensity depression will be produced by lack of emitting matter. And this is always going to be there. And so because it's smaller than this guy here, I think this is what makes you distinguish boson stars from black holes.
Sorry, Jean-Pierre, also your audio is very disturbed. So I think that, you can continue this afterwards and let Luciano go to his class. Sorry, Jean-Pierre, but I cannot hear what you say. So anyway, so thank you very much, Luciano. Again, excellent. We really appreciate it a lot. And now I think that Irina will say something, perhaps.
No, I'm just stopping the recording.